Okay, good afternoon. So today we'll continue on the topic of address translation, and I'm hoping to go through it all today, but we probably won't be able to, so we'll see. Okay, so last time the topic that we discussed was uniprocessor, sorry, uniprogramming, the first class of operating systems where the operating system was kind of like just a system library, and at any given time there was only a single process running in the system. We discussed the fact that in this kind of system, protection is less important because there is only a single process, and the operating system itself is not that important. So in such system, there was no notion of virtual memory. The process that was running had access to the entire physical memory address. The second generation of operating systems were called multi-programming operating systems. In this one, we had a notion of operating system. It kind of like a monitor was what it was called. And then the operating system would at any given time be able to bring multiple processes, multiple processes to run on the system. Now, earlier, or one of the first versions of multi-programming was without any protection. So each process would be mapped to a certain location in the physical memory, but then there was no protection. Again, very similar to the uniprogramming model. All processes had access to the entire physical address. Obviously, in this model that is in front of you, there is no notion of protection, because any process can alter data in any other process, and also the operating system. So there is no protection in this model. Now, a very prominent example for this model was Microsoft Windows. Earlier versions of this, earlier versions of Microsoft Windows had this model. This model soon showed itself as to be not enough for all the reasons that are obvious. So people started thinking about providing memory protection. One of the first ideas that came to mind was keep the notion of allowing processes to use physical memory, but limit their accesses to a certain range of physical addresses. So the architecture that was introduced in hardware was to add two registers, two special registers called base and limit. Every time the operating system starts running a process, the operating system sets the base and the limit registers, and the process that is going to run can only access memory addresses within the range from base to base plus limit, or if the limit is an absolute limit, then from base to limit. So so in this case, as you can see, if process 2 is mapped to base address 20000, and if we want to give this process access to certain range, then we set the limit register to that range. So this is the size of the memory range. So in essence, any physical address between base and base plus limit was allowed. So any physical address between this range is going to be allowed. Anytime the process wanted to access anything beyond this range, then there would be an exception raised by hardware indicating that the process is accessing data that it's not supposed to. So it was the job of the operating system to set these two registers. Basically, operating system had to decide where to map each process and then give them access to. Before I continue, if we discuss this model, one thing that you have to consider is, going back to the discussion we had with regard to compilers and linkers and all of that. It is in this model, it is important for the compiler to know exactly what physical range this program is going to be used, right? Because everything is you're going to create these addresses. I mean, the compiler probably doesn't need to, but when you load your executable image, you have to go and yeah, I take it back. So the compiler doesn't need to know, right? But at the linkage time and at the load time, you have to go and set all the addresses in your code to this range that is allocated to you. So you have to do some work to set these the addresses in your code to be within this range. Now, this model, because of obvious problems that we will actually talk about in more details about, was not sufficient. So the next way of people providing protection was through virtual memory. Now, with virtual memory, we're going to allow the process to create any address within its range of virtual addresses. Let's say, when is the load time? I'm assuming that somebody's asking about the load time. So I'm referring to this figure here from the previous lecture. So basically, at this time, when you want to load your program, you have your loaded module. So now at this time, you probably know which range you're going to be running. So you have to go and set all the addresses in your code to be within that range. So that's what I was pointing to. Okay, going back. So the way we're going to use virtual addresses to provide protection is by mapping different ranges of virtual address from different processes to different ranges of physical address. And if each process creates its own virtual addresses, then there is no way for a process to access a memory region that is mapped to another process. Because this, as long as we can keep this map protected, as long as the process doesn't have access to alter this map, then we can just map regions of virtual addresses to regions of physical address. And by doing so, as long as the way we're mapping, we're not mapping two regions to this two virtual address regions to the same physical address, then there is no sharing. And if sharing is needed, then we can do that, the mapping in a protected way. So the benefit of this is that now the compiler, the loader, they don't need to know where the code is mapped in physical memory like before. So the loader doesn't need to know where this code is going to go. It can always generate memory addresses from 0 to 2 to 32, for example, right? So the loader and linker and the compiler can independent from where this code is going to run or be mapped, generate code. So that's a plus. We can provide protection, right? We can protect the operating system from processes by basically not mapping anything from process to the memory that is allocated to the operating system. This also allows us to have memory sharing. So if we want two processes to share memory, then we can map their virtual address ranges to the same physical address, and that way they can share memory. So this gives us everything that we wanted. So this is a great tool to provide protection. The downside is we'll have to do a translation. So if my program, my process is generating virtual address, eventually I'm going to go to physical memory and read data or write to physical memory. So I need a physical address. So this creates the need for translating from virtual memory addresses to physical memory addresses. So now I have added a step for every access I have to memory. So I need a translation. Now this translation comes with a performance cost because I need to do some extra tasks to access memory, basically translate the address. And as always, we're going to rely on hardware to make this faster. So this would also mean that the hardware should add extra logic to make this translation faster. We'll talk about this later on in this lecture, what hardware is exactly doing for us. The first and basically the easiest translation is called base and bound. It's very, very similar to the multi-programming model that we saw with base and limit registers. We're going to just use the base and bound registers a little bit differently from the previous model. In particular, our process is going to generate virtual addresses. So in the previous model, process would generate physical address, and all we needed to do was to check that this physical address that is generated is less than base. Is more than base and less than base plus limit. So the process was generating physical address. Now, in this new model, base and bound, the process is generating virtual address. So we need to translate virtual address to physical address. If I'm going to map my program, my process to a range, let's say from 10000 to 110000. So this is going to be the base. This is going to be the starting address of my process, and this is going to be the end of it. So how can I translate this 0 to 0x1000? Well, all I need to do is to add 0x1000 to everything, right? So I can set my base and bound. So this is very similar to before. The base and limit registers, these are the same. It's just how we're going to use it that is different. The way we're going to use it is every address that is generated, I'm going to check it with the bound. So I need this address to be less than the bound because my addresses are generated from 0 to the max. All I need to do is to check that any address I'm generating is less than the limit or the bound. And if it is more, then I will raise exception. If it is not, then I will add it to the base. And here I have my translation. So here I got virtual address. I translated to physical address. Again, compare this with before. Before, we didn't have any notion of virtual address. The process was generating physical address. And all I needed to do was to check it with base and bound. Now, process generates virtual address, and all I need to do is check it with bound but add it to the base to get my translation. So this is good because the benefit of virtual address is that your compiler, your loader, your linker, they don't need to care about where your code is going to be in the memory. They can just always generate memory addresses from 0 to whatever the max is. The program you get is going to be mapped to a contiguous region of physical memory because you have a base and a bound. So it's assumed that every address you generate is added to the base. So everything should be sequentially mapped to the physical memory. Your virtual addresses do not change if you change the mapping in your physical memory, right? There is an independence between virtual addresses and physical addresses. The upside of this is, well, we can get protection. So the mission is accomplished. Protection is provided. And the translation has a really low overhead. All we're doing is to add a register to every address that we want to translate. And that's all we need to do. That's our translation. So the translation is just addition. The downsides are quite few. Actually, whatever downside I'm going to mention here, we have with base and limit in the multi-programming model. So most of these issues show up there as well. Okay, so the first pair of problem is this expandable heap and stack, right? So what happens if your heap and stack expands? In base and bound, initially you allocate a certain region of physical memory to your program. Now, heap and stack could grow, and at some point they might meet each other. Now, if they want to expand further, then you have a problem, because if your stack expands, it's going to go and mess up your heap. If your heap expands, it's going to go and mess up with your stack. So you have to do something about this. The solution is, okay, I need to allocate a bigger chunk of memory to my program. That's fine. I can find a bigger chunk of physical memory that is free and give it to my program. But how is my program supposed to use that? Well, I need to copy everything to this new chunk. I have to copy the heap. I have to copy the stack. I have to copy the data. I have to copy the code. And once all of it is done, I go and set the new base and the new limit. And then I go back to my program and I continue. So it's doable, right? So in BNB, you could potentially have expandable heap and stack, but it's extremely expensive to implement. Extremely expensive means that you're going to, copy your entire process address space every time your heap and your stack meet. Now, the other issue this has is memory sharing between processes is practically impossible. Now, theoretically, you could, have base and bound, basically B plus B, of two processes. So this is B1 and then B2. So I could potentially make two processes share a certain range by checking, by setting their base and bounds in such a way that there is a shared interval between the two. But is this usable in terms of physical, in terms of memory layout? The answer is not really. So if you remember, the bottom of my address space is my code. And the top of my address space is my stack. So even though I can make these two intervals have a shared, these two address spaces have shared intervals, I'm going to be mapping different segments of each process to each other. So in my map, I'm going to map the stack of one process to the code of another process. So this is not a useful sharing because, you know, when the process 2 writes to its stack, it basically destroys the code for process 1. And this is not useful, right? So memory sharing is theoretically possible, but practically not possible. All your addresses have to be kind of yeah. So every time you want to move your what is it called? I'm so sorry. Excuse me. Okay, I'm so sorry. I have to be honest. I absolutely do not remember what I meant by this bullet, so I'm gonna just skip over that bullet. The last problem with BNB is memory fragmentation. Now, the issue with fragmentation. Now, let's actually talk about fragmentation. So, do I have slides for fragmentation? Yeah. So we have two types of fragmentation. There is the external memory fragmentation and there is internal memory fragmentation. With external memory fragmentation, I have unallocated memory, but I cannot use it. With internal memory fragmentation, I have allocated memory to someone who is not using it. So these are two types of fragmentation. Now with BNB, I get external memory fragmentation. Here is an example. So let's say I have in my current setting, I have my operating system, process 5, 2, and 6. Now let's say process 2 terminates. I'm going to free the memory for process 2. Let's say at this point process 9 comes in, and let's assume that I'm allocating things with the first the first fit algorithm. So process 9 has the memory it needs. Let's say later on process 10 comes and process 5 terminates. So process 10 gets to run to be after process 9, and now process 5 is terminated. Now at this point my memory is fragmented. I have two regions of memory that are free, but at two different places. They're not consecutive. This means that if I get a process that is big or bigger than any of the two, but less than the total, I won't be able to allocate it. So this is called external fragmentation. Now, obviously, based on bound has this issue, right? So because different processes have different sizes, you're having external fragmentation is unavoidable. Now, because of all the downsides of BNB, the next method that we're going to talk about is a little bit complicated, but it's going to address some of the issues that we had with BNB. In particular, we're going to focus on sharing. So we're going to address the issue that we had with base and bound, which was we were not able to share memory. So we're going to solve that. But in the process, we're not going to solve all the issues. So we're going to see a bunch of different methods to eventually solve all these problems. So we're going to just iterate on our methods to eventually solve all these problems. Okay, so the second method that we're going to talk about is multi-segment address translation. Now, this the idea is to just use based and bound, but instead of using based and bound on your entire virtual address space, you can divide your address space to different segments, like your code segment, your data segment, your heap segment, and your stack segment, for example, and have a separate base and bound for each segment. Instead of having a single base and a single bound for each process, we're going to have a single base and single bound for each segment of each process. So this means that we're going to have a segment map. For every segment, we have a segment number, and for every segment, I have a base and I have a bound. So when I get my virtual address space, when I get my virtual address, I'm going to use the highest bits to recognize which segment this address belongs to. So I'm going to use that to index into my segment map. And once I do, I get the base, I get the bound, I can check the offset, which is the remaining bits of my virtual address. I check it with the bound. If it is above the bound, I raise exception. If not, I add that to the base and I get my physical address. So with multi-segment address translation, we kept the simplicity of just adding base and bound. So basically adding the base to the offset, but we added an extra step, which is dividing the virtual address space to different segments. So we have to first go to this table now to find the relative or the respective base and bound, and once we find, then we can translate our address. So so this segment map is basically similar to the base and bound register. It's a data structure that is implemented by a bunch of registers inside your processor. So your processor has the segment map. And right, so you know, I guess I described how we're going to use the segment map. Now, here's an example of this segment map in action. So I'm giving you the segment map content here. Let's assume that we have only 4 different segments. Segment 0 is a code. Segment 1 is data. Segment 2, we're going to use it to I don't know, do sharing. And segment 3 is going to be a stack. Now, in this particular example, I'm assuming that virtual address is 16 bits. So from bit 0 to bit 15. If I only have 4 segments, this means that I need 2 bits to find the segment number. So I'm going to use the highest 2 bits, bit 15 and bit 14, to recognize or identify my segment number. And the rest of it is going to be used for my offset. Okay, now let's just run an example. So if I look at this address, oh, by the way, I don't exactly know if you're familiar with hexadecimal representation. So basically, when you have this 0x00 F1, for example, so this is hexadecimal representation. What it means is that each number is going to be mapped to 4 bits. So 0 is going to be represented with 4 bits. It's going to be 0, 0, 0, 0. Then the next one also with 4 bits, 0, 0, 0, 0. Then the next one is F. So F is 1, 1, 1, 1. And then lastly, 1 is going to be 0, 0, 0, 1. So this basically gives me 16 bits. Right? So each number in hexadecimal is representing 4 bits. So if I have 4 numbers, that would be 4 times 4, 16 bits. Okay, so now let's look at this address. The first one, 0, 0, 0, 0. So the highest 2 bits are 0, 0. So this is going to be the first one. So we can look at the translation. So the base for this guy is 400, and the size is 800. So it goes from 400 to 4,000 to 4,800. You can do the same thing for every segment that you have. So let's do this one. So what is 4 in 4 bits? It's going to be 0, 1, 0, 0. So that's 4. So if I look at the first 2 bits, it's going to be 0, 1. So it's the data segment. And the base for this one is 4,800. So it goes from here. The size is 140. So it goes to 5C00. And so on and so forth. Okay. Here is an example of running a code. So what you can see here is virtual address. So let's assume that PC is pointing to 0240 initially, right? So let's assume that at the point that we're executing this code, PC is pointing to the first instruction. So PC has the virtual address that we want. And let's assume that we are given this map. So what do we do? The first thing we have to do, let me remove this. So the first thing that we have to do is to fetch this address. So PC is pointing to an address. The first thing we need to do is to fetch it. Okay, so we have to go to memory virtual address 0240. Well, I have to translate this to know where in physical memory I have to go and read this instruction. Okay, if I want to translate, it's easy to see that this is segment 0. If you look at the first 2 bits here, so 0 is 0000, 4 bits 0. So that's the first segment. So I know that this is segment, the first segment. The bits for the offset are 240 in hexadecimal. So my offset is 240. I can check. So after I index into my segment table, I can find that this is a code. I can check that 240 is less than the limit. The limit is 800, and 240 is less than that, so that's good. Now, in order for me to translate, I get the base, I add it to my offset. So that gives me 4,240 as my physical address. Now I can go to physical memory, this address, and read the instruction. So I read the instruction. The instruction is LA A0 VARX. So VARX is the address for VARX is 4050. This basically means that I'm going to put in register A0 the number 0x4050. So basically I decode this instruction and then I execute it. The execution of this means that I'm going to put 4050 into A0, this register A0. Okay, so we're done with this instruction. Then we do PC equals PC plus 4. So we do that. We're going to execute the next instruction. Now, again, to execute the next instruction, we need to do another translation. So this time PC is pointing to 244 to 0244. The translation is as before. We do that translation. The instruction we get is a jump strlen. So this means that PC register now has to have strlen. So strlen address is this. So PC will be set to 0x0360. So this becomes the PC, right? Now, next instruction, we have to decode, we have to translate 0360 because that's our PC. Again, this is a code segment. 360 is less than 800. And the way we're going to translate this is going to be 4360. So that's our physical address. We're going to go there and read the instruction. So the instruction is going to be load in V0 0. Okay, so when we execute this instruction, we're going to set the V0 register to be 0. We're going to set it to 0. So after we decode it, that's what's going to happen. Then PC goes next. Again, we have to translate. We do the translation. I'm not going to spend time on that. We execute. Now we read this next instruction, which is LB T0. Now, this is a load from memory because we're going to go to address that corresponds to the content of A0. Now, this is the content of A0. So we're going to go to the memory with the address 4050. Okay, now we need another translation. So this is an instruction with two translations. The first translation happened for PC to just fetch the instruction. The second translation is now happening to do a load. We have to bring data from memory. So let's translate this guy. What is 4? If you write 4 in 4 bits, it's going to be 0100. Now, if you look at the first 2 bits, it's going to be 01. So it's a data segment. The base is 4800. The offset here is 50, and 50 is less than 1400. So we're fine with that. So all we need to do now to translate this is to add 050 to 4800. So the address we get is basically, so this is our offset. The address we get is, this is our base, and this is our offset. So the translation is 4850. So we just translated this. And now we can go to memory and set T0 to be whatever is in that memory, space. Okay. And then we do PC equals PC plus 4 and so on and so forth. So this is an example of running code and using the multi-segment address translation. Okay, let's have a discussion on this. With address, with multi-segment address translation, we basically use the semantic of segments. We said that our code has different segments, and we can just map each segment to a consecutive physical memory region. Now, there are holes between different segments, as we saw, for example, in this figure. Let's see. So, for example, in this one that we can see, there are holes between different segments, right? As you can see here, these are holes between different segments that I have in my virtual memory. So if you access a virtual memory address inside this hole, you're going to get segmentation fault. So you probably have dealt with segmentation faults in the past in your journey to become good software engineers or computer engineers. So segmentation faults happen when you access a virtual address that is outside the allocated segment to you. That's where you get segmentation fault. Now, not all accesses to these holes would have to lead to segmentation fault. So for example, if the segment in question is a stack and your stack has to grow, so maybe you have a recursive call and your stack needs to grow, then you might end up doing a stack pointer minus minus, and that might be beyond the allocated stack segment. At that point, the first thing that happens is that the hardware is going to detect that you're accessing something beyond what the segment table is set. It's then hardware is going to wake up the operating system and say a segment fault has happened. Now, operating system looks at the content and the context of this fault, and it might recognize that, okay, this is okay. I'm going to allocate more memory to the stack. So operating system could do that. Now, this part is tricky. Let's say, this is your memory, and this is where your stack segment is mapped to physical memory. If you have extra memory after that is free, all you need to do is to basically change the limit. So you can just change the bound for this segment because you can just extend it that way. But what if you have another region allocated right after stack? So in this case, there is no free memory after the stack, so you can't just add to the bound. What you have to do is to find another region large enough to copy your oldest stack and maybe increase the bound, and then set the new base and the new bound for your stack segment. So dealing with this segment fault could be tricky, depending on how your memory looks like at the time that this happens. The same with heap, right? If you need more memory, you might go beyond what is allocated to you. The operating system has to handle those situations. Every time you have a context switch, you have to set the segment table. So, for the new process that is going to run, you have new mapping. So you have new base and bound for different segments. Now, what happens to the old one? You have to save it somewhere. One option is to save it in your PCB, for example. Now, this the segmentation resolves the issue of sharing, because if I want to share, for example, code segment, I can simply give the same base and bound to two different processes for their code segment, and that way they can share the code on the physical memory. So this addresses that issue. The other thing that we kind of mitigate is the issue of external fragmentation. Now, in base and bound, our memory allocations were for the entire process, and the entire process, the virtual memory range for entire process was big. Now we have in the segmentation, we have divided the entire process into different segments, and now each segment is smaller. So we have less chance to get to a situation where a new segment is needed and I don't have enough space for that, but we haven't entirely gotten rid of it. So external fragmentation still exists because different segments have different sizes. So as long as your allocations are at different sizes, you're going to have external fragmentation because you might have free memory, but in different locations of your physical memory and not sequentially. And the request that you're getting might be bigger than any single free memory region. And at that case, you're going to reject that. So external fragmentation. But it's less likely to happen because your segments are smaller compared to base and bound, where your allocations were at granularity of processes. Okay, but it still exists. So our next topic, our next method for memory translation is going to address external fragmentation. External fragmentation is going to be resolved only if all your memory requests are of the same size. So in that case, if you have memory available, then you can allocate it, because all of your memory allocations and deallocations are with the same size. So that's the idea behind paging. We're going to divide our physical memory and virtual memory to the same size units, and this is going to be the unit of our allocation. So every time we want to allocate, we're going to allocate one page, and then another page, and then another page. And every time we want to free memory, we're going to free a page, and another page, and another page. So as long as I have one page free, then I can allocate one page. So there is no issue with external fragmentation. This, however, creates a possibility that I might have internal fragmentation. I might allocate a page to a process, but the process might not use the entire page. So we're trading off external fragmentation with internal fragmentation. We're solving external fragmentation by having same size units of memory, but this will create internal fragmentation in return. It could, depending on the size of our pages. Okay, so we're going to divide our memory into fixed size chunks. Now, this also helps us in memory management, right? When everything is the same size, then I can, for each for each page in my physical memory, I can represent it with a single bit if I want to know if that page is allocated or not. So, if I have 100 pages in my physical memory, then I can represent them with 100 bits. The ones that are allocated, I can set their bits to 1. The ones that are not allocated, I can set their bits to 0. Now, I can search now this bitmap. So this is called a bitmap. Every time I get a new request for a new page, I can just find a 0 in this bitmap, and that would be the page that I'm going to allocate. Now, the more, the larger your pages are, the less pages you have, because your physical memory is fixed, the size of it. The larger the size is, the higher the probability of you getting internal fragmentation, because you're going to allocate a big chunk for each request, and there's a chance that the request does not need the entire allocated memory, and that therefore you get internal fragmentation. But again, the bigger your pages are, the easier the management becomes because you have less of them. So management becomes easier, internal fragmentation becomes worse. Now, let's look at how we can use the idea of paging in address translation. So the problem of translating virtual address to physical address becomes translating virtual page number to physical page number. I have divided my physical memory into physical pages. I have divided my virtual memory to virtual pages. Now, if I want to translate, all I need to do is to translate virtual page number to physical page number. That happens by looking at your virtual address and then looking at the size of your page. If each page, let's say your pages are, let's say, I don't know, 4 kilobytes. So if you have 4 kilobyte pages, this means that you have 2 to 12 bytes per page. Now, don't forget that each memory access is to a single byte. So you're reading a byte or you're writing to a byte. So the granularity of addressing memory is in bytes. Now that we have a page that has 4 kilobytes, if I know where my page is, I still need to find my byte, the byte that I'm interested in. So I need 12 bits to find the byte within each page. If each page is 4 kilobytes, for example. So for a 4 kilobyte page, I need 12 bits to find a specific byte that I'm interested in. So I look at the page size and I say, okay, so I need a certain number of bits to find my byte. Those certain number of bits are your offsets. So the offset is basically the index into the page. So I'm going to use the rest of my virtual memory to have my virtual page number. So once I translate virtual page to physical page, then I use the offset to find the particular byte that I'm interested in. To do the translation, I'm going to need a table. So this is called page table. It has a virtual page number to physical page number. I need a pointer to point to this physical page, sorry, to this page table. This register is set by the operating system. So every time you context switch, you have to set this pointer to point to the page table of the process that you want to run. You get your virtual page, you check it with the page size, page table size. If it is more than the page table size, you have an exception. If it is less, then you can index into your page table. You can find your translation. Once you have your physical page number, you can copy your offset, and that gives you address to physical memory. So that's how we're going to translate. So there is no addition this time. It's kind of we just do a mapping between virtual page numbers to physical page numbers, and we write that down inside our page table. I got a question. Won't you need to check if offset is less than the max size of page? Well, you don't need to do that checking because you're recognizing the offset by the size of your pages. So any system has its own defined page size. So whatever your page size is, you recognize or you identify how many bits you need for that page size. Again, if you have 4 kilobytes, you need 12 bits. If you have 1 kilobyte pages, then you need 10 bits. So the number of bits for offset is uniquely identified by the size of your page. So the bigger your page is, the more bits you need for your offset. And then anything other than the offset becomes your virtual page number. Hopefully that answered the question. Okay, so here is an example. So the number of bits that you need for offset is dictated by the size of your page. The remaining bits are used for virtual page number, and then once you find your physical page number, you just copy it. You append it with the offset to find your physical memory, physical address. Let's run an example. Excuse me. Okay, so suppose that I have a system with 8 bits of address bus. So my virtual addresses are 8 bits. Let's assume that this page size is 4 bytes. So if I have 4 bytes, I need 2 bits for offset. So this translates to 2 bits for offset. Okay, so every memory address that I have, I'm going to translate it. So let me fix my. Okay, so let's look at the first one here. This is going to be 0, 0, 0, 0, and then 0, 0, 0, 0. Now 2 bits are going to be offset. The rest of it is going to be virtual page number. Okay, so this virtual page number is 0. So I go to my page table. I get the translation. The translation is 4. So what is 4 in hexadecimal? Sorry, in bits? It's going to be 0, 1, 0, and then offset is 0, 0. So this is my physical address. So if I were to do this in hexadecimal, the first 4 bits, that is going to be a 8, and then the rest just zeros. So 0. So this is going to go here. I guess I have the slides. Oh, what mistake did I make? Oh, I did this mistake again. Oh, so my bad. So I did a bad job in translating 4. So 4 is 0, 1. Is 1, 0, 0. So this is 4, not 1, 0. And then I put the offset, which is 0, 0. Now the first 4 bits are going to be 0. The second 4 bits are going to be 1. So it's going to be mapped here. Now let's look at another one. Let's translate this one, the next one. So this one is 0, 0, 0, 0, and then 4, which is 1, 0, 0, 0. The first 2 bits are offset. The rest of them are virtual page number. Now, what is this number? That's 2, right? 1, 0, that's 2. So it's going to be mapped. Am I again making a mistake? I am. So sorry, 4 is 0, 1. God, so bad. Excuse me. So 4 is 0, 0, 1, 0. So this is 1. It's going to be this guy. So the translation is 3. So 3 is 1, 1. And then the offset was 0, 0. So that is, and then the rest of them, we just appended with zeros. So that's 0. And then this is C. It's 8 plus 4, 12. That's C. So it's going to be mapped here. Yeah. And then the last one is 8. 8 is 0, 0, 0, 1. Am I right? Yes. And then 0, 0, 0, 0, 0. 2 first bits are offset. The rest of them are virtual address. This one is 3. Sorry, it's 2. So I go to this one. The translation is 1. So 1. And then the offset was 0, 0. And then I append the rest of it with zeros. So that would be a 4 and a 0. So this is translated to here. Okay, so you can actually do the translation for different things. I'm gonna jump over them, but if you're interested, you can just look at translating these guys using this table. So as you can see, like end result, let me get rid of everything here, make it clean. So what is happening here is that each one of these virtual pages are mapped to corresponding physical pages. So each one of them is mapped to different physical pages, right? And the physical pages don't need to be having the same order as virtual pages, right? They could be anywhere in the physical memory. Okay. Now, what is in this page table that we talked about? Each page table entry has a pointer to the physical page, right? So each one of them has a physical page number. Obviously, that's the main purpose, right? We wanted to translate from virtual page number to physical page number. So we have to have that physical page number. So that's a pointer to the actual page in physical memory. That's the first thing that it has to have. The other things that it could have is a valid bit, a read only or write, read and write or write only bit, so that we can have permissions for each page. And now the permission could then mean different use cases. In this case, I have the read, the write, and the execute permissions. Now, if all 3 bits are 1 or are set, so if a memory page, if a physical page has a read, write, and execute permission, this could be a code or a data, so you can do whatever you want with this one. It was common, but it's no longer common because it has security risks. So if this allows the program to write code and then execute it. So this is kind of dynamic code generation. So you can dynamically generate code, and that has shown to have security risks. So you can write and then execute that code, and that's bad because obviously you could, mess up with the system, but with the code that is not monitored. The other thing you can do is to set read and write. So this is very common. You could have read and write access to your data. The other one is read and execute. This is also common. Usually for your code, you have read and execute. You can read your code and then execute it. Read only is also very common, usually used for data. You have read only access. Write and execute is not used. The other thing that you could have is a write only permission. This one is used usually for device drivers. So, a device has a device controller, and the device controller has its own registers. For example, your display, you could have commands sent to your display to refresh or to change certain parameters. Now, the commands set some registers. These registers are usually mapped to certain addresses, and those addresses you can just write to them. and writing to those addresses basically means sending commands to your device. You usually shouldn't read those because they're just registers that are controlled by the device, and usually you shouldn't count on them having, meaningful data, and you probably have dealt with some of those in your boards, but write only permission is usually used for those registers where you're communicating with the device by the device driver. Lastly, you could have just execute permission. So if you don't, for example, want your code to be read and just to be executed, this could be used. It's not that common. And if you don't grant any permission, this could be used as a guard. So any access to this memory would cause an exception. So for example, one use case for this is, if you remember, we were talking about how you can protect a stack of one thread from another one. So one solution that I suggested was to, write to certain addresses between the boundaries of two stack. And if one stack is going to overflow to the other one, it's going to override that parameter or that value that you have written. So you can check that value every time and make sure that it exists. The other thing you can do is to put these guards. So every time the thread is trying to write or read those boundaries, it will raise an exception. Okay, so here are how permissions could be used in action. Not just the permission, but also the valid invalid bit that we talked about. So one is demand paging. So if you remember from 252, when you're when you didn't have enough memory, you could swap a process to your permanent storage. Now, when that happens, you can just make all the page table entries for this process invalid, because previously they were mapped to these physical pages. Now that you're swapping these physical pages to your permanent storage, then the translation is no longer valid. So you can make all those translations invalid when you do demand paging. It's called demand paging. I'm not sure if you get to know it with this name, but the name is demand paging. We'll actually talk about it in a little bit more details later on. The other thing that we can do is copy and write. If you remember with forks, the child and the parent, the parent process and the child process could share the memory. But if you remember, I said it doesn't make sense to create the copy right away, so you can make them share. Now, one way to do this is to make the entire region read-only. If any of the parent or the child tries to change the contents of the memory, then you can raise exception and then do the copy. Finally, we can have another example, zero fill on demand. So this happens when you're allocating memory. Usually you want to write zeros to memory so that, if this memory was allocated to another process and that other process maybe stored a password or a key or something sensitive in that memory region, and then deallocated it, and now this memory is being allocated to another process, it doesn't make sense to not clean the data. But it also doesn't make sense to clean the data every time that the memory is allocated, because it could well be the case that the process doesn't even end up using that memory region. So what you could do for that situation is you can not give any permission to that region that you allocate initially. and once the process accesses the allocation, then you can zero it down, right? So it's kind of like a lazy zero, lazy cleaning of the memory. So you wait, you wait until it becomes necessary. Once it becomes necessary, then you can clean the data. So you either make it invalid or you don't give any permission, for example. So both of them are possible. Okay, so now with this paging, we can see that sharing is possible. So two different processes could share the same physical page. So this is an example. So I have process A, I have process B. Now in process A, I mapped virtual page 1 to physical page 5. And in process B, I'm mapping virtual page 0 to physical page 5. And this means that this physical page 5 is shared between these two processes. They're using different virtual addresses. As you can see, they have different virtual addresses because each one of them has a different virtual page number, but they're accessing the same physical page. So sharing is possible at the granularity of physical pages. Here is an example of page table. Let's say that, I guess in this example, each page is 8 bytes. So I'm putting aside 3 bits for the offset, and the rest of the bits are used for virtual page number. So I have 5 bits. How many page table entries do I need? I need 2 to 5, which is 32 entries. So my page table will have to have 32 entries, as you can see here. These are the 32 entries. As you can see, there are these holes that we talked about when we were talking about segmentation. We talked about these holes that exist in the virtual address layout. Now, the holes that are not allocated, their page table entries are just set to 0 or set to null. So these are the regions that the pages that I'm not using, right? So the pages I'm not using, I don't have anything in the page table entry. These are basically invalid page table entries because the virtual page is not mapped to any physical page. And the ones that are valid, they have the translation. So the virtual page number is translated to physical page number in that entry. Now, let's say if my stack is going to grow, right? So I'm going to use 2 more pages for my stack. All I need to do is to map these 2 virtual pages that I'm going to use to corresponding physical pages. So I can just go and search and find 2 pages in my physical memory, let's say these 2, and then I can just map them by setting my page table to point to those. Now, one thing to note is the size of this page table. So the size of this page table is basically the size of my virtual, the number of virtual pages that I could have. So in this particular example, because I was using 5 bits for my virtual page number, this was 2 to 5. Now, if I'm using, I don't know, 20 bits, then the size of page table should be 2 to 20 entries, right? So this is challenging, right? So this page table could become really huge. It exponentially gets bigger as the number of bits for virtual page number increases. The size of this page table exponentially grows. It's 2 to the number of bits that I'm using for my virtual page number. Okay. So every time I context switch, I need to make this page table pointer to point to the new page table, and also I need to change this page table size. Now, how big is each page table? That depends on how many address bits you have and how big your page is. So let's say if you have 4 kilobyte pages, then you will need 12 bits for your offset. Now, if you have 32 bits for your address, this means that 20 bits are left for virtual page. So you're going to have 2 to 20 entries. Now, let's assume that each page table entry is 4 bytes. Then you're going to need 4 megabyte for your page table. Now, in a 64-bit system, again with a 4 kilobyte page, you need 12 bits for your offset. That means that you have 52 bits left. And if I'm not mistaken, this is probably more than the number of atoms in the universe. So you're going to have one entry for each virtual. Actually, let's check. I don't exactly know what's the number of atoms in the universe. Oh, it's much bigger than that. So sorry. So it's less. But it's close. I mean, not that close, but it's a big number anyhow. So the number of atoms in the universe is much bigger than that number. But anyhow, you get my point. It's a big number. Going back. So, and if let's say each one of them is 8 bytes, then you need 32 petabytes for your page table. And this already is bigger than any available DRAM that you can buy today. So a single page table would need more space than your entire physical memory. So this means that this flat page table is just not practical. So we have to resolve this issue. Now, one solution that you could have is to, okay, so what are the good things about this? Well, it gives us a simple memory allocation because you have paged the memory and you can have that bitmap. It makes it easy for you to share pages between processes. The downside is basically the first one is that this inefficient use of a space. So even for the pages that you're not using, the virtual pages that you're not using, so going back to this figure, so for all these virtual pages that you're not using, you still need to have a page table entry for all of them. So you're not using them, but you have to have page table entry for those. So the size of your page table is not proportional to the size of virtual pages that you're using. It's basically fixed to the maximum number of virtual pages that you could be using. So in the next lecture, we'll see how we can bring this down and make the size of page table to be proportional to the number of virtual pages that I'm actually using. And I usually are, for your programs, you're using a lot less than your maximum, a lot less. So we're going to bring the size of page table down. Okay, so one way is to make this page table, our pages bigger. Instead of 4 kilobyte, I can have bigger pages, maybe 1 megabyte pages. But then that would lead to internal fragmentation. Okay, so let's pause here. On Tuesday, we're going to talk about we're going to talk about other methods that we can use. Now, one update is that unfortunately the pool was vetoed, so more than one of you voted to have final. So we're going to have final because I didn't get the consensus and the agreement from the entire class. So I will send an email to the entire class with that update as well. Talk to you on Tuesday. Take care, be safe, and bye.